The Farlands. 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 Farlands.
You might have heard of the Minecraft Farlands, a phenomenon in Minecraft that occurs when you travel to distances so great, the terrain generation itself breaks down entirely. While this has been patched since version beta 1.8, if you do manage to reach those same kind of distances, you will still experience a jitter, and more extremely, the further out you go. There seems to be growing issues when the number go big, and Minecraft isn't the only game that suffers from this. In Roblox, if we are 500,000 studs away from the origin, we start to see the same signs of jittering. Here's 1 million studs away from the origin. At 2 million studs, textures start to distort. At 5 million studs from the origin, at least in the X direction, you can no longer move along the X axis, but can still move along the Z axis since your Z coordinate is still relatively small. Now here's 10 million. And 20 million. As you can see, everything is totally bugged. Many other large-scale or open-world games can also suffer from this graphical glitch if they don't take measures to solve it. Kerbal Space Program, or KSP, for example, uses a floating origin technique. The origin, 000, remains fixed on the player, while the environment moves around them. Because all objects nearby the player have small coordinates relative to the player, they completely avoid the graphical glitches introduced from massive numbers. Minecraft inhibits you from reaching massive numbers in the first place by incorporating a world border at 30 million blocks. If you use commands to try to teleport further than that, invalid position. If you use commands to try to move the world border itself, double must not be more than 5.99E7. If you want to go further, you have to use external tools. Infinite Chess is a game I've been working on for years. Its rules are identical to classical chess, except the board is infinite, and pawns are still allowed to promote at their original ranks, 1 and 8. Infinite. Infinite. That word has a lot of expectations behind it. Is infinite chess actually infinite? Surely it's gotta suffer from some of the same glitches. It can't actually be infinite. That's just impossible. And today, that's what we're gonna find out. How big is the infinite chess chessboard? Right off the bat, if we just start zooming out, we reach our first bigger board, for lack of a better term. There's going to be infinitely many of these, and each successive one is exactly 1,000 times wider than the previous. These ones here are exactly 1,000 by 1,000 squares. They're just meant to help you get a sense of your positioning, as otherwise the board would just be monochrome, and it would be difficult to tell if you were zooming in or out. I could have instead rendered grid lines, but I thought checkerboards looked cooler. We continue zooming out, and we hit our next board. Each of these squares are 1 million by 1 million squares wide. And we hit our first roadblock. Our zooming is getting slower and slower. No problem, I can just disable the line of code that added that feature. And we should be good. For the sake of this video, I also added a display in the corner showing us our scale, which is an internal game variable representing how shrunken down everything is, and our screen width, which is an after estimation of how many squares fit across our screen at any given moment. They're in shorthand scientific notation. This E followed by the negative sign means we should actually shift the decimal place that many digits to the left. And this E followed by the positive sign means we should shift the decimal point that many digits to the right. That's a lot of zeros. We've already stretched over an undecillion squares across our screen. If this was in real-world meters, we would have already traveled outside our universe and into countless parallel universes. And we're gonna need to speed things up so we can reach our first interesting behavior. We've now stretched over a Google squares across our screen. There's a Google Googles. And 1 centillion squares. At E308, the board stops rendering, and apparently our screen width estimation has become infinity. If we try to draw arrows at this distance, there seems to be a bounding box of which we can't draw outside of. If we keep going from here, our scale gradually loses precision until it becomes just 1 digit of precision. At this point, it changes much more slowly, eventually reaching a minimum of 5e-324. And we also see the occasional error in the console cannot set scale to 0. That seems to be the limit, and it does allow us to zoom back in, so it hasn't quite crashed. If we were to stop zooming out right before the board stops rendering and venture out a little bit, we do reach the intriguing stripe lands, where our x-coordinate has become infinity. Here we can no longer move along the x-axis, but we can still move along the y-axis and zoom in and out. Okay, so E-324 appears to be our zoom limit, or E-308 until glitches start happening, but I have a confession. The game has fooled us thus far. While it seems fine and dandy up to a scale of E-308, if we were to zoom in at this distance, the glitches we would experience would be wild. The board isn't actually this big, but where is that dividing line if there is one? Let's start again, but this time we'll regularly check to see if we're able to move that distance. At the thousands and millions, there's no trouble. Even the billions and trillions don't pose any issues. It's only at the quadrillions where things start to look grim with the first signs of jittering. Here, my Y movement is jittery, and if I'm zoomed in enough, I'm unable to move along the Y axis at all except by dragging. Things are only gonna get worse from here. At 10 quadrillion, our zooming is focused on the edge of the screen. Our ghost piece snaps to every second square, and the piece doesn't even appear centered on a square. In addition, our legal move highlights are totally crooked, and the arrows pointing to pieces currently not visible are not lining up properly along the edge of the screen. At 100 quadrillion, our ghost piece now snaps to every 16th square. We are now completely unable to move along the y-axis. Our diagonal legal moves don't even show up unless we're zoomed out enough. And the arrows are even more misaligned. This one's remained largely a secret, but starting at 10 quadrillion, there's this glitch called phasing, where you can phase through pieces a certain distance. Here we are giving a phase check through the night. At 100 quadrillion, we can phase up to 7 squares through a piece. Here's us giving another phase check through 7 pieces. Going further, at 1 quintillion squares, there appears to only be one highlighted square on the screen legal to move to. The arrows are now aligned permanently to the middle of the screen. Our legal moves don't even render unless we're very zoomed out. This bigger board is even experiencing jitter. At the origin, the impression is we can only move to 1 square, but our true legal moves reveal themselves after zooming out a bit. And we can now phase up to 64 squares through a piece. Let's dive a little into why the phase glitch is happening. Up here are the generated legal moves of the piece. What we're interested in is its 0-1 vector, because that's its up and down movement. And it tells us we can slide downward infinite squares, but we can only slide upward 100 quadrillion, 957 trillion, 119 billion, 186 million, 309,100 squares. If we use the same JavaScript engine to add that to its current position, we get 16? Okay, that's as high as we can appear to move, but if we were to plug this into a big number calculator, we would get 10. That would bring us to this level, but even that is incorrect. If we were actually blocked on the night square, then we should only be able to slide upward 100 quadrillion, 957 trillion, 119 billion, 186 million, 309,099 squares upward. But okay, attempting to represent that number in the JavaScript engine just snaps it back to 100. The numbers this big like to do that, don't they? And we'll learn why that is later in the video. Let's keep going. 1 sextillion is where our legal move lines start to break down. At this distance, if we try to move along both axes instead of just one, then our zooming is focused on the corner instead of the edge, the arrows are completely absent, and no matter what we do, we can't click to move to this only legal move on screen. But if we were to first align ourselves on the diagonal intersecting 0, 0, then we are able to move on the diagonal. At a scale of E-156, our hover queen doesn't render on the legal move lines anymore, and clicking them sort of freezes our game. But we can recover by clicking the pieces. We can also no longer drag the board at this distance, but we are still able to move around with WASD. Another wild thing you can do is swap the color of your bishops. One bishop can spend a few moves to hike across the universe into the area of the board where snapping occurs, and when he returns, he is now his antimatter counterpart, the dark square bishop. Now I have 2 dark square bishops. Now, since clicking the legal move line no longer transitions you down, it's a little harder to continue moving greater distances, but I can still see what it would be like by loading game codes with pieces having already moved that far. I also missed this earlier, but ever since the trillions, we can only draw horizontal arrows. Beyond this point, there was no meaningful change in the graphics, so let's jump all the way to 1.79E308, which was the furthest move of which I could still load a game. Beyond that, and I get an error due to the coordinate becoming infinity. This is just after the scale where the board stops rendering, and it sits right on the edge of that invisible box that we can still draw arrows inside. If our camera moves outside of this box even slightly, our coordinates become infinity again and we return to the stripe lands. So, this is it. This is the end of the infinite chessboard. We look beyond and see a vast expanse of squares that will never be reached, destined to never receive the pleasure of upholding a chess piece. Not even -7, -179,000 centillions, 5,379. To get the total area of the board, all we have to do is multiply by 2 and square it, which gives us a total area of 3.23E600.
Hold up, that can't be accurate. Even at 10 quadrillion, we can only move to every other square. This snapping thing has to reduce the area.
You're right. If we're accounting for that, this is not the correct area of squares actually movable to. I think it's finally time we learn what's going on with these numbers. IEEE 754 double precision floating point is the specification for standard JavaScript numbers. Double precision, 64 bits. 64, a very finite amount to store one number. Already we're going to run into issues. 1 bit stores the sign. It determines whether it's positive or negative. The next 11 bits are the exponent. And the last 52 store the mantissa. To get the number being stored, we add 1 to the mantissa as a binary fraction, then multiply that by 2 to the exponent minus 1023. This system does have a ton of benefits. They can store really small numbers, or really massive numbers. But there's a catch. The larger the number gets, the fewer precision you get in the decimals. Think of it like at any given point, we have a fixed number of digits for precision. If our number is small, a lot of that precision is used towards the fractional part. However, if it's big enough, imagine imaginary zeros appended after the mantissa. We simply don't have control over what these digits are. This is the cause of the snapping and glitches so many games experience. When the number gets big enough, we just lose the ability to store precision at the smaller scales. For this specification, the value number.maxSafeInteger is key to understand. At this point, all the mantissa can do is store the precision of these digits, but there's nothing left to store any fractional part. If we add 1, we get the next number up. This is the first unsafe integer, because if we add 1 again, it snaps back down. We have to add 2 to get the next storable value. We have lost the ability to store all odd numbers. We experienced this at 10 quadrillion when our ghost piece started snapping to every second square. And the culmination of this is an infinite chessboard of movable 2 squares of expanding grids spreading further and further apart. Until eventually we reach the limit of the specification itself, 1.79E308 number.max value, before we overflow to infinity. And after a little bit of math, which I'm not going to show the details of, the final area of the infinite chessboard's movable 2 squares is about 77 undecillion. What was I thinking? I should have called my game Finite Chess. At least that would have been accurate. 77 undecillion isn't even close to infinity. It's 0 compared to it. Here I am deceiving everybody saying the board is infinite when it's clearly not. It's not. It's not. I have failed. We are still trapped here in this mortal realm, unable to escape, forever destined to live out our puny lives. Is there not more? Is there not more? There has to be. I won't believe it. And this video isn't over yet. What can we do then? What are our options? What about that floating origin technique that KSP uses? Yeah, I already do. Back in 2022, when I was working on the first release, the board used to be significantly smaller. We're talking glitches as short as the millions. Sure, it wasn't infinite to begin with, but that small was completely unacceptable to me. So, not knowing what the concept was called, I figured out if I fixed the camera in place and only moved the board underneath it, I could get vastly more unglitchy terrain from it. And to be fair, this did help a ton. But why hasn't it solved it? To understand why, GPUs don't render with double precision floats. They render with single precision ones, only 32 bits. For half the cost, they have significantly less precision, and a smaller upper bound than 64-bit floats. What fixing the camera in place essentially does is it brings all the geometry data of the scene down within Float 32's bounds before sending them to the GPU. But for the CPU to do the math to bring that data down, it has to start from somewhere higher. And if we start from somewhere high enough, then Float 64s, which is what the CPU's JavaScript engine is working with, aren't capable enough to prevent precision loss when performing that arithmetic. Essentially, what we've done is increase the limits from Float 32s to Float 64s. And that's good. We'll keep using the floating origin technique. But we need to somehow prevent precision loss when converting the scene's geometry data from extremely high numbers to within Float 32 bounds. Obviously, we can't use these floating point numbers anymore. They're flawed for our use case. What can we use then? Int 8s, Int 16s, Int 32s? All of these have hard bit limits too, so they're out of the question. But there is one interesting data type JavaScript has, the big int. Big ints don't have a limit, they can be arbitrarily large. This sounds perfect for us, but there's a problem. Big ints only store, well, integers. Anything after the decimal point just gets truncated. While they are satisfactory for storing piece coordinates, since those are only at integer increments, there are two very important game variables we absolutely do need decimal precision for. They are your position and your scale. If your position isn't capable of storing decimals, then it would snap to every integer, recreating more jitter we experienced earlier. But our position may be arbitrarily large too, so neither floating point numbers nor big ints work for us there. But if we somehow had decimal precision, we could probably get away with a fixed number of decimal digits. The second important game variable that requires decimal precision is your scale. As we continue zooming out, that becomes arbitrarily small, and we can't have that truncating to 0. For this variable, we need behavior more like a shifting mantissa, a fixed number of bits of precision, but at an arbitrary depth inside the fractional part. What can we do? There are no other built-in JavaScript data types that fits our requirements, which means we'll have to look outside for a solution. Perhaps we could use a library like decimal.js or bignumber.js. These provide a software solution for numbers of arbitrary precision, which is what we need. But I wasn't satisfied with their speed. Heck, the more someone zooms out, the more digits of precision we need. It scales linearly with time spent zooming out. Players are going to hit FPS drops so quickly. I need something that is going to be fast. You know, big ints are one of the fastest ways to perform arbitrarily large integer arithmetic. I have an idea. What if I took a big int and borrowed some of its bits to represent a simulated decimal portion? This could allow us to have any amount of decimal precision we want. And since it's all stored inside the big int itself, it has no upper bound. It was at this point I decided to write my own library. Here's how it's going to work. Let's call a number in this library a big decimal. Each big decimal is going to have two properties, the big int and the divex. Big int, you can probably guess, is going to store all of the bits of our number. Divex, on the other hand, will tell us where in that bit string, starting from the right-hand side, our imaginary decimal point is positioned. Say we wanted to store 2.25. We set our divex to 2, which places our decimal point here. To the right of that, we put 0, 1, which is binary fraction for 0.25. And to the left, we put 1, 0, which is 2 in binary. That gives us a big int property of 9. Or in other words, given our big int and divex properties, the value of the number it's representing is big int divided by 2 to the divex. This is actually almost identical to how existing floating point number systems work. The big int is like the mantissa, and the divex is like the inverse of the exponent. The main difference is this provides a base of unlimited bits. I need more dynamic behavior from my library though, because the variables storing position and scale needed to be treated differently. Our position needs some decimal bits, but not a lot. We can probably get away with 7 decimal digits. Because we won't be moving the decimal point, this models a fixed point representation. Our scale also needs decimal bits, but the exact amount differs on our current zoom level. We need to be able to move that point around to accommodate the mantissa, so this will model a floating point representation. I had to write custom methods for performing arithmetic between big decimals. Add, subtract, multiply, divide, compare, negate, min, max, floor, seal, the whole shebang. I even had to come back later to write more complicated methods like power, square root, logarithm. They're not simple. But bits of code in the game needed to perform those methods with arbitrary precision, so I had no choice. Also, where applicable, I had to write separate methods for both our fixed point and floating point models, depending on the needs of the variable being worked with. When it was finished, I was satisfied with the performance. Then began the painstaking work of converting the entire code base from using standard floating points to bigints and big decimals. Okay, it's finally compiling. That took like 2 months. I had to fix so many errors and pretty much changed every single file in the entire repo. But I haven't been able to test the code in a long time, and I have no idea what's going to happen, so let's just find out. Okay, it loaded, which is a good sign. Can we start a game? No. Slide limit game rule is in an Okay, I fixed that, so let's try this again. Let's see what happens. Oh, we are able to join a game, but it's frozen. Let's look in the console. Cannot mix bigint and other I'm not giving myself enough credit here. The fact that the board and pieces still rendered after making so many changes, even if it was just for one frame, is a huge accomplishment. Okay, that one should be fixed now too. Let's move on to the next error. Okay, it's not frozen. I don't know if you can see that, but the promotion lines definitely aren't rendered in the correct place, but I'd say this is huge. Like, I can still drag the board and everything. Can I move pieces? Holy, I did not expect it to be working this well so quick off the bat. Okay, the arrow indicators are okay, there's our first crash. Yep, I knew it was gonna happen. So it turns out not all pieces are movable right now. If I click on one of the infinitely sliding pieces, yeah, it crashes. Okay, I fixed the promotion lines. It does let me select infinitely sliding pieces now, but it doesn't render their legal moves, but it does appear they're still calculated correctly. They were not, in fact, calculated correctly. Also, some of these arrows are just pointing in the complete wrong direction. All right, arrows are looking good now. Legal move model generation also looks good now. Okay, we get a crash whenever we try to animate a piece off screen. Okay, that seems fixed. Stacked arrows look good. Ooh, okay, there was a crash there. Division by 0. It looks like this isn't related to the Huygens, but it's related to the distance of the piece the arrow's pointing to. Okay, that is patched. Okay, something's wrong with the Huygens blocking system. This pawn shouldn't be blocking this Huygens. What? So it turns out it was an off by 1 error. I just needed to increment some coordinates at the end of a loop instead of the beginning. That fixes that. Collinear check defenses look correct. Knight riders look good. I can draw arrows, but I can't draw highlights. And drawing rays are bugged too. It's only drawing them in this field of view. Highlights work when zoomed out though. I was calling the wrong function. Now they work. Rays are fixed as well. The bigger boards don't render when we're zoomed out. Fixed. This isn't supposed to happen when the camera is transitioning. Normally it's supposed to be smooth. Yeah, my big decimal exponentiation function was trash, so I rewrote that whole thing. That's more like it. For some reason at this zoom level, using WASD I can move around normally, but as soon as I start dragging the board it becomes jittery. Insufficient material works fine. So does the 50 move rule. There's still some jitter going on when animating huge distances. Fix that. Okay, yeah, practice checkmates don't work. How about now? Where's the board? That looks crazy. It was an issue with how I was rendering the world border when it was at extreme distances. I know the mention of a world border seems counterintuitive to what I'm trying to do, but this will only be enabled in engine games because they can't use big integers and shouldn't use big integers so that they can remain faster. The engine does not want to make a move. Big ints can't be JSON stringified. Updated my replacer and reviver. Oh, that was lucky. That was a one move mate. And it's moving now. Seems to work fine. Highlight lines work. Snapping seems to work well too. Do online games work? I think so. Making pre-moves doesn't highlight them. I was calling the same wrong function. Now they highlight. Work just fine as well. If we just start zooming out, it abruptly stops. That was due to me calling the wrong big decimal multiply function. No more stopping. Now there were more bugs I fixed off recording I chose not to include, but one thing I want to add with this update is psychedelic after effects applied to the board the further you travel from the origin, as if you're peeling back the layers of reality. If the board is no longer glitchy, I guess I'll just have to add the glitch manually. What on earth? That's a cool effect, but not quite what I'm searching for. This keeps getting more interesting. That's what I'm going for. But not so intense. I'm not going to spoil the final effects I chose to include because I want you to discover that organically for yourself, but I'm very satisfied with them. And now, the part you've all been waiting for. Let's go! 10 to the 300. 10 to the 500. 10 to the 1,000. I literally can't zoom faster than this. The variable is no longer having an effect on the zoom speed. There's the culprit. 10 to the 3,000. 10 to the 5,000. I think it's slowing down. I think my FPS is dropping. 10 to the 10,000. Highlights work. Arrows work. Arrow that stretches 10 to the 10,000 squares across your screen works. Moving 10 to the 10,000 squares away. Ooh, crash.
Oh my god, bro. Oh, hell no, man. What the?
Oh. Nope, not crash, just a lag spike. Works. Snapping. Working. First checkmate from over 10 to the 10,000 squares away. Oh, forgot something. Sometimes this is harder than it seems. Oh, okay, there we go. Checkmate. I have to redo that, that was horrible. First checkmate from 10 to the 10,000 squares. Works. Okay, this might be dangerous, but I'm going to try teleporting 10 to the 100,000 squares out. It works seamlessly. Let me try this. Okay, yeah, I'm at 1 FPS up here. That's a lot of millions. While zoomed in though, it isn't that bad. Moving works, but it is inherently glitchy. As a final test, checkmate from 10 to the 1 million squares away. It is not handling this well. Nope, wait. Pick it up, pick it up. Wait, yes. Checkmate! There it is. So I never found a hard limit. Rather, the further I went, the lower and lower my frames became, until it became unplayable. It seems likely the practical limit depends on your specific machine. If you have a faster CPU and more memory, you are just going to be able to reach further without frame drops. But assuming that computer power wasn't an issue, if we wanted to know the real hard limit, what would it be? Well, when I told you guys that big ints don't have an upper bound, I actually lied. They do have a limit, but it's not because of a design limitation. It's in place only to prevent you from blowing up the world with your PC in it. The V8 JavaScript engine allows big ints to have up to 1 billion bits before throwing the size exceeded error. This is absolutely huge, equivalent to a number over 300 million digits long. To store a single max valued big int would take 128 megabytes. Forget doing arithmetic with that much data in the span of a single frame, and many big int operations have to be done every frame. But nonetheless, this still gives us a hard limit. With this information, we know for a fact that the total area of the new infinite chessboard is not over 7.05 E646 million squares. So it's not infinite, but we already knew that. As long as we live in this universe, there will always be limits. Infinite chess, truly infinite chess, can't exist here. But maybe there's a universe or dimension it can. I want to thank these 13 people you see here. They're among my biggest supporters on Patreon. I've spent thousands of cumulative hours on this project, and time isn't free. Because I want Infinite Chess to be accessible to as big of an audience as possible, I released it free to you. Unfortunately, that's not very smart financially for me. If you would like to support me, this project, and this channel, signing up for one of my Patreon plans is the best way to do that right now. By signing up, you will receive recognition in the outro of every video I make, as you see here, recognition on infinitechess.org itself, of which I'm planning to redesign, and a unique role on the community Discord server. Seriously, thank you all for your support. Especially Andreas and Idontus. They're among my most consistent code contributors. Since going open source, there has been massive progress made. We've added Night Riders, Huygens, custom themes, practice checkmate puzzles, ranked, arrow drawing, snapping, pre-moving, and more. I'm not slowing down either. I have big ambitions for this project. This website's looking a little bland. Maybe I'll modernize it next, make some room for what games I have planned on this finite board. Anyway, that's it for me. Thank you for watching. My name is Naviary. Until next time.